review session on the recent conference on the consciousness, models for consciousness held in Stanford.
Yeah, so this is just showing the invited speakers, just to give everybody their place. I think we can move on actually and go to some of the things I thought might be interesting to discuss more directly. So again, I was just there for one day. Yeah, but Kobe's talk was interesting. And there were several talks that went to this direction, which I found interesting. So there's this whole notion in quantum physics that consciousness might be fundamental, in that there's this weird transition from describing things abstractly, mathematically in Hilbert space, such as the probability distribution where an electron may be at any point in time in space. And then when you do a measurement, well, it behaves like a particle. And so now it has a discrete point in space. And so the question is, what is a measurement or observation? And mathematically, there's no formalism associated. And so Eugene Wigner and actually John von Neumann and other people early on said, well, maybe consciousness does that. And so now there's more and more people that hop on the bandwagon of that because IIT provides an avenue to maybe empirically test that. And so I know that David Chalmers has work on that, and Johannes Kleiner and several other people are working on that. But what I found the most interesting aspect of that was that, and it was almost mentioned offhandedly, is that might mean that we can never get complicated quantum computers to work. So what I mean is that if those two things are true, that consciousness collapses the wave function. So it basically makes measurements all the time. And so you can't have a Schrödinger's cat because you're looking into the box all the time. And if it's true that IIT, if you have a minimal phi that is consciousness, that would mean that if you build more complex quantum computers, at some point you will start having systems that will have an ever so slightly small phi, and they would constantly collapse the wave function. And so the advantage of quantum computers would go away. And so basically, because that will happen in the next couple of years, that's an empirical experiment that's waiting to happen. And in a way, it's like a strange threat to the program of building quantum computers. I didn't trigger a bigger discussion, but I thought that's actually really something interesting to talk and think about.
Yeah, so this is related to, I was talking about before about Johannes and Eric's paper about falsification in consciousness. And we were talking about how IIT sees consciousness as a structure, but it doesn't really have like a function or like a causal role beyond like pre-existing physics in a sense. The other side is if you think consciousness does have some sort of function, like essentially it implies like new physics in a sense, then Kobe's paper was about how really the only avenue that's left for you is that consciousness is somehow influencing quantum collapse. And we should make clear this is very different from like the orchestrated objective reduction idea from Hameroff and Penrose. So this is a different idea entirely. This is just that consciousness somehow has to be influencing collapse and is related to measurement. And yeah, so Kobe's idea is that like if this is true, then some sort of ordered structure should influence the rate at which collapse happens, or to some degree, and that will influence whether particular kinds of quantum computers can be built. I tried to ask him in a little bit more detail about what he really meant by structure and whether that was just like entropy or it was phi or whether it was something else. And he said like he's not clear on that as of yet. That's the sort of details that would have to be worked out. But that's his prediction. And that's sort of the idea that if you think that you can do science of consciousness and you think that like in some sense consciousness will actually make an impact on the dynamical trajectory of the evolution of states of the world, then this is the sort of thing that you're left forced to say might happen as a result of consciousness. So that was, yeah, I thought it was a cool talk too.
But I don't really understand this logic here, because first of all, isn't there at least some kind of quantum computers already existing?
So I think they're up to like,
argument is that it's.
I think they're up to like 50 qubits or something.
You just can't, yeah, okay. Oh, cannot
the idea
scale.
Yeah, the idea is at some scaling point, you would see that your quantum computers like failed to cohere the expected number of qubits that you would think. So basically, like as your system scales up, you would think that it would continue to work well, and you could go from 50 qubits to 100 qubits to 1,000 qubits to 1,000,000 qubits, and like you expect some certain level of error based on their physical properties. And instead, what you would see is that you like kept having a failure of like, I don't know what, I'm not a physicist, so I don't know if it's coherence or position or whatever the technical term is. But the idea is there would be an unexpected failure of the system. And then you'd have to be like, oh, maybe it's because it's like measuring itself in some sense. And the measuring itself would stop the superposition which is required for it to work as a quantum computer. Or entanglement. Okay. Yeah, I'm going to mangle it, but that's the general idea. Ask Kobe if you want more detail.
Yeah, maybe as we are not the expert in this field, maybe we can move on.
Yeah, this is actually somewhat related. So that was a talk, Aaron, you might have missed that actually, that I thought was interesting as well. So there's been this debate about dissociating consciousness from intelligence. Christoph spoke did that really well. And so there's this notion that a regular computer, just the ones that we're using right now, is using the von Neumann architecture shown here to the left. And because it's feed-forward only, so that's related to the unfolding argument, it shouldn't have phi. And so we can't have AI conscious because the underlying physical system has no integrated information. And so there's this talk by somebody's getting their degree in computer science who got interested in that. And his point was that that's not true. And so this is shown here on the right-hand side, which is RAM, or it's a diagram, basically the electronic diagram, how RAM functions. And so his point was that whenever you run a program, what's physically happening in the computer is basically changing all of these little switches. And that amounts to changing the causal structure of the system. So Larissa Albantakis seems to be partly in charge of this program as well. But that was a really surprising, interesting take that, well, if you take IIT seriously, then yeah, even a regular computer should have a minimal amount of phi.
Was this Jonathan Simpson's talk?
Correct, yeah.
Yeah, I'm sad I missed it. I look forward to seeing it. I had to chair the session in the other room. But it did look fascinating. So the talks will all be online later, so we can have a look later.
Isn't it the same kind of a line of the research that has been going on in IIT for maybe 10 years or something like that to compute the actual RAM's, phi? And it used to be pursued by one PhD student there. I just forgot his name, but maybe this paper should have been written for a long time, but not out yet, because they are now probably perfecting this or reanalyzing this in the IIT 4.0 framework. But the point was that there was a really small and also independent and unconnected, very, very small phi everywhere. And it's not really like, that doesn't have any structure for each of this big phi, right?
Yeah, I think that's
architecture.
Yeah, I think that's correct. But it's interesting that even a simple statement such as, well, a regular computer doesn't have phi, according to IIT, and so therefore it's not conscious. AI wouldn't be conscious. As always, I think we have to be more careful. And so I found that really intriguing. And it also shows, I think that was one of the things that I really appreciate about this conference, how interdisciplinary this research has become. That you have neuroscientists, you have philosophers, you have quantum physicists, and also computer scientists. Everybody sitting together working on the theory. So that this is really quite exciting and interesting to see.
I see. Okay.
Yeah, so this I just put in because I think was also interesting. So Lucia Meloni gave a really excellent talk on her research program with the adversarial collaboration. And of course, at the end, everybody was asking, well, how far are we? How far are we? And so my understanding is that, yeah, it's might already be halfway or even more than halfway done in terms of the data collection. And that's really impressive, given that COVID happened, which obviously makes data collection hard, and the ambitiousness of this research program. So yeah, that's another really intriguing progress that should happen. It seems anytime soon that we might learn Well, IIT or global neuronal workspace theory, which one comes out ahead?
Well, there's some problems with that, though, which came up during the discussion session. So yeah, Lucia was talking about how there might be data out, I think either late this year or early next year, at least from the first phases. But she showed the set of experiments and hypotheses that are working. And it's called an adversarial collaboration, but they're not all set up to be like directly adversarial, was basically what she was talking about, where there's various hypotheses, but they're sort of for each theory semi-independently, rather than like a specific hypothesis which will only be possible to support one theory or the other. So there's a serious risk that like all of the theories will come out like basically reasonably supported by the data that they are currently collecting. And somebody was like, if that's the case, then like, what's the point of this adversarial collaboration? And she was saying that mainly the idea is to like get this sort of framework going and get people engaged in this sort of system. And obviously, like, there's the chance that the current theories might be invalidated by the current experiments. But there's a lot of enthusiasm from her and from others about essentially the next round of experiments to come after this current set, where there would be more work to try and make sure that the hypotheses are like actually properly, completely adversarial, that we can't just have everyone winning, which I found interesting as well.
Yeah, that was well put.
I mean, yeah. I'm also involved in a discussion, not really in terms of the experiment, but the comparison of the IIT and predictive coding camps. And it's very difficult. It's just super difficult to come up with any kind of hypothesis that, both theory actually care or make some kind of strong prediction, right? And also, this was really well articulated in Nicolo Negro's, paper on Lakatoshian framework of the science, rather than this Thomas Kuhn's kind of paradigm shift or some other falsification kind of framework. But each theory has a very strong core hypothesis or core ideas, and then within from that you have an sort of associated, corollary kind of hypothesis, and most likely this adversarial collaboration will need to align these two completely different theories to the close, extent, so that this corollary or peripheral prediction kind of touch each other. So even if that the peripheral prediction doesn't actually work really well, it doesn't mean that the entire theory has to be completely rejected. So I think this kind of idea, Lakatoshian idea, needs to be also more broadcasted to the science community, to think about what it means to have this hypothesis testing or theory as a body of the science, and then what do we do to make a progress in science.
Yeah, Lucia had some great slides that I think some work that some of her students had been doing, or that she'd been doing, which she started her talk with, that essentially ran through how they could predict which particular camp the people running writing a particular paper were from before they'd even seen the results, just based on methodological choices, which was just implying that these different camps are so distinct from each other that they all even use different methods and have different ideas and different starting assumptions, and they're not really properly talking to each other necessarily, which is problematic when you're trying to develop adversarial collaborations. And this is related, I think, to the conference, because one of the criticisms that I heard people make about the conference entirely, and let's say about the Association for Mathematical Consciousness Science, is what even is the point of this group? We already have the Association for the Scientific Study of Consciousness, the ASSC. What can the AMCS deliver that the ASSC doesn't already do? And I think this is an example where something that I think the AMCS is quite good for is in trying to come up with real mathematical, clear formalizations of the theories and really trying to nail it down. It will hopefully help people make very clear what their assumptions are and what their framework is, and whether or not they actually, even in principle, can be made to be like to make different empirical predictions about the world. That's kind of why I was excited about the conference, is it was nice to see people really try and formalize these sorts of things.
Yeah, so that's also, maybe let me go. So the reason why I started to also, appreciate this kind of, viewpoint or strategy or philosophy is partly because I've been over the several months working on the quantum cognition prediction about the Bell inequality and the violation of that in a psychophysical setting. And as I learn more about this Bell inequality violation, it becomes really clear that quantum mechanics or quantum theories have been already developed and pretty much over there in 1920s, but its interpretation or position of the science has been very mixed until Bell came up with this inequality test theoretically, and then finally tested empirically that it does violate. So even the quantum mechanics, I think it took probably like 60 years from the initial proposal of the theory, and then I think after that probably 20 or 40 years until the Bell came up with the inequality, and then further 20 years for the experimentalists to test it, right? We are now much faster in terms of scientific progress or scientific framework, so we can possibly expect something like that to happen within our lifetime. But that's a sort of prior experience that humans had about these kind of big theoretical ideas and how to test it. So I don't think expecting just one single adversarial collaboration to resolve one or the other is just so unrealistic. It's just a super good direction in general.
Yeah, I agree with both of you very much, and I'm only slowly catching up to all of this. So I also think that the history of quantum physics is really instructive in this case, because they had two theories for the longest time. One was describing everything continuously with Schrödinger's wave equation, and then they had also the matrix-based math. And eventually it was mathematicians that figured out, well, that's equivalent. And I think it was Lenore Bloom who also brought it up after Lucia's talk, that it's possible that these theories are orthogonal to each other. It's possible that they are equivalent. So we might find out that these theories are not quite as mutually exclusive as we maybe right now think they are. But in order for that to happen, they will have to be fully formalized. That is the power of math. And so maybe that might bring us to the last slide, which is that another interesting thing that I thought is happening, that again, I learned from you now, using this innovative mathematical notation of string diagrams or process theories, which I think comes from something that Roger Penrose came up with a long time ago. And so here's the book by Bob Koch about using this kind of diagrammatic language or mathematical notation to describe quantum physics. And now Chantal and Johannes Kleiner using that to describe IIT. Going beyond, at this conference, Sean presented using that exact same formalism to describe predictive coding and the free energy principle. And there was one slide that I found really remarkable, where on the left-hand side, there were all of these equations by Carl Friston, combining Bayesian theorem with long, big equations, a whole bunch of them. And then to the right-hand side, there were just these simplified diagrams that are, again, mathematically equivalent. And it boiled down to, I think, 5 boxes and 6 spaghettis between them. And so that I find really exciting, that not only do we have now this work on formalizing things mathematically, but also trying different notations. And in this case, having the same formalism for IIT and predictive coding. And so that is where we maybe slowly approach that point where we can directly merge these theories, see how the different domains or different predictions might differ. And yes, you could do this with equations as well. But for somebody like me who's actually really bad at math, this right here is quite intriguing.
Yeah, this, I don't know whether this is actually true or not, but Bob Cook claims in this book that with this approach, any elementary school student or even kindergarten kids can understand the quantum theory, right? Better than university students with full of equations to understand the quantum mechanics. I think they tried some kind of study on understanding the quantum theory with this approach or mathematics approach, and I don't know the results.
Yeah, I would be really interested in trying this, for example, with IIT. So it's something that I pondered trying this semester, maybe even dividing a class in half. And one half would provide the equations that we showed in the beginning of today, and then the other half we just walk through with this diagrammatic language and see just didactically, pedagogically, which works better. And so for me, the answer I think is pretty clear. So equations are hard for me, but this is, I think, one of the things that is intriguing about math and this conference, that there's more to it. And so this, again, I was just there for one day, and but that was another highlight for me that I find really intriguing.
Yeah, I think, I'm also, I don't know whether this is true for all the mathematicians or scientists or not, but in general, if I remember correctly, people tend to be either like visually oriented or auditory oriented or logically oriented in terms of understanding of thoughts, right? And then I'm more visual, definitely, and so I tend to draw the diagram and explain these ideas with this kind of thing. And one big advantage of this type of diagram thinking or diagram understanding or explanation is that many things can happen simultaneously or parallelly, right? Whereas if I need to speak or read to understand mathematics, it's usually serial kind of thinking. And people's understanding and the intuition comes from both, establishment of the parallel, like, Kahneman system 1 understanding and also system 2. So yeah, having something like that is much more memorable, first of all. And also, second of all, is that, you can pay attention and work through it by yourself by, it looks like this one is similar to this part, but some kind of additional thing is happening here, and then going into like this, a battery-like thing, and so coming from the battery-like thing, what is that? So this kind of thing is more intuitively also curious and elicits some kind of intellectual curiosity. So maybe that's more attuned to the human intelligence from the developmental perspective and so educational perspective as well. Maybe we need both to do that.
Yeah, the second thing I find interesting here is I pressed Sean on that directly, which is that, well, the benefit of equations is that you can directly translate that into Python code. And that is one of the strengths of IIT, that if you have data, you can run it through the algorithm based on the math, based on the equations, and you get an output. But what the heck do I do with this, right? And so I think that's a common objection also of using category theory in consciousness research, that, well, I can do something with the concept of a function, but what do I do with a functor? So can you write that in computer code? And so he said, yes, basically, because applied category theory is this big growing field, there is the beginnings of a Python package where you can basically start to code just using these diagrams. And I think that is where this might really take off. So if you imagine taking predictive coding and you're basically creating this wire diagram in a way, and it becomes runnable code that makes that you can actually use quantitatively, and then you do the same for IIT. This is where I think we could really start directly test theories more directly. And I think what's already getting clear here is, for example, that, yeah, what does predictive coding really have to do with consciousness, and what is similar to IIT? So both of them, for example, seem to be having a discrete notion of time, states. For a Bayesian account, you have priors built on the past, and you're updating that based on the present. And so IIT obviously does that with the cause repertoire. And so there are some similarities already there between the theories that I think come out of the formalism once you use that notation that might not have been fully clear beforehand. And so, yeah, that goes exactly what I think Aria was just saying, that what's exciting about this conference and this crowd is that these conceptual breakthroughs happening with that level of rigor. I could really see, if it's not doing it already, is advancing the field.
Yeah, so I think, what you talked about is a class of the programming language called the functional programming, right? Some of them is like Haskell is probably most famous. I'm not super familiar with that, but this Haskell language is designed to deal with this kind of functorial kind of ideas where you input and also output the functions in itself. So basically, you give without really collapsing this kind of internal structure, like into a dot, but keeping this kind of structure as structure, you can combine this component with something else like this way, and then to see how it behaves as a sort of the whole. So it's a very nice way to compose many different kind of complicated structure. And also one big area of the application is this, decentralized computation, which is more likely to be applicable for the biological function of the nervous system as well, right? Right now, almost every computation neuroscience simulation is based on the central clock governing all the time, and also governing the noise that's happening across the different neurons, and the update is done simultaneously or sequentially. But in reality, no physical system is like that. But if you imagine that one neuron can be represented as one single computer node, and then connected with that one with another node like this way or that way, then that's much more similar kind of simulation or sort of the understanding of how the neural system actually works in real time. So to do that, we also need this kind of theoretical tools. We can build from the sort of the parts to the whole, but also starting from a whole, we can also zoom into the component without a loss of information. So I think that's a next generation kind of both computational theory and also neuroscience using this type of math. Yeah. All right. So that's the last slide, I think.
Yeah. If you two have a little bit more time, I'd be really curious to hear what happened at the rest of the conference from Ariel, if something stuck out in his thoughts.
Yeah, I'm curious also.
All right, I'll give a few other highlights of stuff that I remember hearing. Apologies to anyone I've missed out. It's like I don't have the schedule up ahead of me, and I didn't manage to get to all the talks because there were parallel streams at different times. Other highlights I remember are, I think her name was Carolyn Jennings, gave a good talk about emergence. And like this was more of a philosophy talk about different kinds of emergence, and strong emergence and weak emergence and contextual emergence, that maybe is really well known in the philosophy literature, but it was a bit new to me, like the different conceptualizations, which I found helpful, where like strong emergence is the idea that you like put parts together and you get something more than the sum of its parts, like strictly more. Weak emergence is like where you get some sort of behavior that like looks like it's emergent, but is like actually still just a property of its parts. But she sort of goes into a more formal description. Yeah, that's Carolyn Jennings. That's right. Okay. So it was good, and she gave.
She used to work on the attention and consciousness, I think.
Yeah, I think she mentioned that that's what she works on too. But I found it interesting because it triggered a whole bunch of discussion amongst different people. And an argument I particularly enjoyed overhearing, but I wasn't qualified to judge, is there were two quantum physicists arguing with each other about whether entanglement counts as an example of strong emergence or not. And I can only say that they didn't seem to agree by the time they ran out of time. So it's just like these ideas are relevant to consciousness, but also to other areas as well. So that was one. Another talk that was good, I think, was, so Johannes Kleiner, we've mentioned a few times, gave a talk about formalizing what we mean by quality spaces. And I think he's going to have a paper out on this sometime soon. But he basically just briefly went over the idea of quality spaces as presented by David Rosenthal and Austin Clarke, and like these previous ideas of like there's individual quales and there's relationships between them and they're linked to stimuli. But he was essentially just giving a more like fundamental mathematical description of what they would be. And maybe that's less interesting to everyone else, but it's definitely interesting to me and us now, because that's what we're working on to a large degree. So it would be nice to see like a formalization of that. Who else did I think was particularly good? There was also just a collection of like talks on various reasonably interesting but random collections of stuff. So there were talks on there was one talk on the self. There were a few talks on free energy principle and relationship to consciousness. There was a good talk on anesthesia and slow waves in relation to anesthesia and like better prediction of like the level of anesthesia of patients. There was, I guess, like a little bit less formal mathematical frameworks, but was still interesting to hear. Then there was just a lot of good discussion, I think, like during the social events and sorts of things, where it was nice to hear like people talking to each other and like different camps talking to each other. Like there was quite a lot of discussion about the phenomenology first approach. So like me and Camillo Signorelli and Johannes and a couple of other people were talking about this, even though there wasn't like a formal presentation on it during the conference. It was definitely something that came up again and again, and its relationship to IIT and other ideas that I found useful. There was also, emergence definitely came up quite a few times. That was interesting. And then there was sort of like just the meta level, which we talked about with relation to Lucia's talk, but just like what can actually be done with these mathematical frameworks and what they can contribute came up again and again and again. And like which camps need to be speaking to each other. So there was a bit of, quite a number of the younger people I spoke to talk about their frustration with more seasoned PIs. They felt like who were too entrenched in their camps and insufficiently like sort of trying to take on a collaborative spirit of like, well, consciousness science is still really young. All of these theories might be completely wrong. We need to like talk to each other a bit more and sort of agree with each other and work through each other's problems. And that I found also, I think, helpful and interesting. I mean, there was also like meta-theoretical discussion around why that's the case and just how the funding is still really limited for this field generally, which sort of probably pushes people to like have their particular camps because they have to fight for their funding. But yeah, it was interesting on a number of different grounds. That's probably all I think I can remember.
Okay. That sounds all good. Is there anything else, Alex or Ariel?
Not for me.
Yeah, last thought I have is I met several graduate students at that meeting, and shout out to them. But also I find that particularly exciting that there's now mathematicians joining consciousness research, and there seems to be excitement again among a lot of young students that are entering the field, noticing that there's development, and it reminds me a little bit of maybe of now when we were young. So it's very exciting to see that that this is happening. So again, for me, this was a very invigorating meeting, and I can't wait for the next one.
We are still young, this is the youngest day of our life, rest of our life, anyway, we definitely want to do something like this in the future, and I'm also kind of working on something. Maybe we can chat about that offline. So, but let's finish the recording here. Thanks, Alex and Rio.